recording is going, no. 9.1 is just an overview, a very, very general overview as to what Chapter 9 is going to be about. It's non-computational. Section 9.2 will become a lot more computational in nature. All right, so testing the difference between two population parameters. Suppose we want to test to see if population means of two different populations are the same or different. Our null hypothesis could look like this, saying that the two unknown population means are equivalent to each other versus they are not equivalent to each other for the alternative statement. Now, both these hypotheses right here are equivalent to these hypotheses right here. They're saying the same thing. Okay. So to say that the difference between our unknown population means is equal to 0 versus not equal to 0 is saying the same thing, that they are equal or they are not equal to each other. Right. That'll also be true when we're testing for two different population proportions for equivalence versus non-equivalence. Our hypotheses are going to be established as such right here. Okay. And, you know, this order of subtraction really doesn't matter when you're conducting a two-tailed test, because you have two rejection regions, one in the lower and one in the upper tail of the normal distribution. So it doesn't matter if you get like a test statistic that is positive or negative. If it falls in a rejection region, it'll either fall in the upper or the lower tail rejection region. So the order of subtraction is not really an issue when conducting a two-tailed test for the difference between two population parameters. It becomes more of an issue when you're dealing with a one-tailed test, okay? Or sometimes called a directional test. And here would be an example of one-tailed tests. Suppose that we were conducting a right-tailed test for the difference between two different population means. This would be a right or an upper tail test, indicated by the symbol used in the alternative statement, greater than. This would be an upper tail test for the difference between population proportions. And both of these indicate lower tail tests for the difference between population means versus proportions here. Okay. So notice, just like when we're testing one proportion or one mean, we have always the equal sign for our null hypothesis statement. And the symbols for our alternative statement, again, are going to be not equal to, greater than, or strictly less than. Okay, so there's really no difference as far as the symbols of our hypotheses are considered. All right. Now, if two samples are independent of each other, then the subject selected from sample one in no way influences the outcome of what is selected from the second sample, and vice versa. All right. Sometimes samples, however, are dependent, in which case what is selected from the first sample does influence what is selected from the second sample. And they give an example of independent samples. An example would be if you selected 25 people for a control group, 25 people for a treatment group. For a medical research experiment, the selections for the control group do not change the probability of what is selected for the treatment group. That would be an example of independent samples. Dependent samples would be, suppose we're comparing the heights of fathers and sons. If you select a person for the sample of sons, their fathers must be in the sample of fathers. And obviously, these samples have a dependency upon one another. just by the biological connection between a father and a son. Okay, so these would be dependent samples here. When we conduct a hypothesis test for two population parameters, or the difference between them, we're going to use the normal distribution to determine our rejection and do not reject regions, and therefore the critical values are going to be z variates, if you will. Okay. The test statistic, just like the test statistic with one population test, is going to be a ratio of the difference between an observed value and the expected value to the standard error of the sampling distribution. All right. When we were testing for one unknown population mean, our sampling distribution was that of all sample means. When we were testing for an unknown population proportion, the sampling distribution was for all sample proportions. Well, that's going to be the case when we're doing hypothesis testing involving two populations. The standard error is still going to be a sampling distribution, okay, of usually the difference between the sample results, sample means or sample proportions. But it's still going to be a sampling distribution, which will be approximately normally distributed, which is an extension of the central limit theorem. So these sampling distributions that were used for one population test are going to be analogous to the sampling distributions used for two population tests. And they both share the same characteristic of being normally distributed. Okay, so that's a broad overview of what our hypotheses are going to look like for the most part when we conduct hypothesis testing involving two populations. So let's go to our textbook and just see if we can do a couple of problems here, just to maybe try to identify what type of hypotheses would be tested in section 9.1. So we're not actually doing the test in 9.1. We're just warming up to this idea of what our hypotheses would look like for a two parameter test here. Okay. All right, so section 9.1. And let's do a couple of these here. For number 5, they want you to state the null and alternative hypothesis for each conjecture. A researcher believes that the mean number of cups of coffee that male college students drink per day is greater than the mean number of cups of coffee that a female college student drinks per day. Okay. So what hypotheses would we be testing here? Would this be a two-tailed test or an upper or a lower tail test? Anybody want to weigh in here?
Upper tail.
Okay. Yeah. Probably going to be an upper tail test because we have the statement greater than. So we're basically testing to see if the mean number of cups of coffee consumed by male college students is greater than that consumed by female college students per day. And so our hypotheses could be set up this way, where mu sub m represents the mean number of cups of coffee consumed by males minus the mean number of cups of coffee consumed by females is equal to 0. And the alternative hypothesis would say that this difference is what? Greater than 0. Okay. So those would be your hypotheses that you'd be testing here. So And the key is that these samples that would be chosen from each of these respective populations would be classified as being independent samples, because there's no relationship between these students here, no biological relationship, etc. So these are independent samples that would be selected here. All right, so that'd be an upper tail test there. Okay. All right, see if you can do problems 6 and 7 now. We'll call this classwork 1. All we want to do is just set up the hypotheses that would be tested, and that's it. All right, so try 6 and 7. All right, for number 6, these would be the hypotheses that we would want to be testing. A nutritionist believes that the mean fiber content of wheat type cereals is higher than the mean fiber content of rice type cereals. So this would be an upper tail test where we would look at the mean fiber content, the difference between the mean fiber contents of these two different types of cereals, wheat versus rice. The null hypothesis says essentially the mean fiber content is not different. Whereas the alternative hypothesis says, yeah, the mean fiber content of wheat-based cereals exceeds the mean fiber content of rice-based cereals. Okay, so these would be the hypotheses that would be warranted for a test like number 6 there. Number 7, researchers believe that children ages 8 to 11 who get an hour of daily exercise perform better on a thinking skills test than those who do not get an hour of daily exercise. So these would be the hypotheses that you want to test, where the mean score on a thinking skills test for those who exercise minus the mean skills score for those that do not exercise, no exercise, would be equal to 0, versus the alternative hypothesis, which says that yes, the mean scores of the 8 to 11-year-olds who get an hour of daily exercise would be greater than the mean scores of those who do not do any exercise. So these would be the hypotheses that you'd probably want to test for number 7 there. Okay. Is that making any sense here? Any questions? All right, go ahead and do number 8 and 9. You can include those also in your classwork, number 8 and 9. See if you can set up the hypotheses.
You're muted.
Sorry about that. So these will be the hypotheses for number 8. to test whether the mean mile per gallon fuel economy a four-wheeler gets compared to the mean MPG for an all-wheel drive is equal to zero, meaning essentially there's no difference, versus the alternative hypothesis, which says that the mean MPG of a four-wheeler would be less than the mean MPG for an all-wheel drive. To say that this difference is less than zero, and notice you're taking this mean of the four-wheelers, subtracting off the mean of the all-wheel, and to say that this difference is less than zero means that you would also be saying synonymously that this mean is less than this mean. Okay? So the mean MPG of four-wheel drives would be less than the mean of all-wheel drives. That would be the alternative hypothesis statement here. 4, number 9, a researcher believes that women who stick to the Mediterranean diet for a year will have fewer strokes than those who are not on the diet. Again, the null statement says that the mean number of strokes experienced by women that are on the Mediterranean diet versus those that are not on the diet would essentially be about the same, no difference. Versus the alternative statement would say that the mean number of strokes a woman experiences being on a Mediterranean diet versus the mean number of strokes that a woman experiences not being on the diet would be less than zero, meaning that the mean number of strokes a Mediterranean diet woman would experience would be less than the mean number of strokes that a non-Mediterranean diet woman would experience. Okay, so these would be the hypotheses you want to test here for 8 and 9 there. All right, so these would be lower tail tests here. Notice that. All right. Number 11 and 12. And 13. Okay, we'll finish up this section by having you do the last classwork out of this section, which is 11, 12, and 13. So go ahead and do those. Just set up the hypotheses for 11, 12, and 13. All right, for number 11. A researcher believes the percentage of emails that are junk and not read by males is greater than the percentage of junk emails that are not read by women. So, the hypotheses. Null hypothesis says essentially there is no difference in the percentage of junk emails read by men and women, versus the alternative hypothesis that says the percentage of junk emails read by men would be greater than the percentage of junk emails read by women. Number 12, environmentalist believes that the percentage of air pollution produced by trucks is less than the percentage of air pollution produced by automobiles. So the null hypothesis says essentially there is no difference regarding the percent of air pollution produced by trucks versus air pollution produced by automobiles. Whereas the alternative hypothesis says the percentage of air pollution produced by trucks is less than the percent of air pollution produced by automobiles. Finally, number 13, the percentage of college graduates who believe that chewing gum improves their memory is not equal to the percentage of high school students. I got high school graduates who believe that chewing gum improves their memory. Essentially, we're testing for difference versus indifference here. Okay, so the null hypothesis would be equal to that. Essentially, there's no difference in the percent who believe chewing gum improves memory, to the alternative hypothesis that says there is a difference in the percentage of college graduates who believe chewing gum makes a difference in memory compared to high school students. Percentage of high school students who believe chewing gum makes a difference is not equal to 0, meaning that these population proportions are not equivalent to each other. Here, we're assuming that they are perhaps equal to each other, but here they're not equal to each other. So this is an upper tail test, lower tail test, and a two-tailed test. Okay. All right. So now that we hopefully understand how to set up these hypotheses a little better, that will enable us to actually conduct hypothesis testing, okay, regarding two populations here. All right. So let's move on to section 9.2 now. In 9.2, we're actually going to, get down to business as far as actually conducting hypothesis testing between two population means. And we're going to conduct a z-test. So when we get done with this section, we will be able to test the difference between two population means using the z-test. These are the overriding assumptions for the z-test to be valid for the difference in population means. Number 1, both samples must be randomly chosen from the respective populations. 2, the samples must be independent of each other. Number 3, the standard deviations of both populations must be known. And that was also the case for a one population test for a mean. Using the z-test, we assumed that we knew the population standard deviation. Of course, if we don't know the population standard deviation, we use the
Sorry, I can't.
What's
We're
that?
looking at your paper. We're looking at your paper, not the screen.
All right, hold on a second. All right, let's go back here. So section 9.2 is going to be testing the difference between two means using a z-test. Okay. And hopefully by the time we get done with this section, we'll be able to conduct that test between two unknown population means for the difference between the two unknown population means, conducting a z-test. In order to conduct a two population z-test, these assumptions must be valid. Both samples are randomly chosen from the respective populations. Both samples are independent of each other. The standard deviations of both populations are known. And that was also true when we did one hypothesis testing for a population mean. If we conducted a z-test, we knew the population standard deviation. If we did not know the population standard deviation, we conducted a t-test. Okay. Number 4, if either sample size is less than 30, the populations must be normally distributed or approximately normally distributed to ensure that the sampling distribution of the differences between all sample means is approximately normally distributed. Okay. Of course, if the parent populations from whence the samples are chosen are normally distributed, then the sample size can be less than size 30. Okay, and then the sampling distribution of the differences between the sample means still will be normally distributed. So a lot of these assumptions were also true for testing one population parameter. So they carry right over into this 2 population parameter test. All right, so this is going to be the test statistic. It is distributed according to the normal distribution, so we call it a z-test variant or z-test statistic. Notice the numerator consists of the difference between the sample means chosen from the respective populations minus the purported difference of the unknown population means under the null hypothesis. So again, this assumption comes from under the null hypothesis here. And it's going to be divided by the standard error. And actually, this is a pooled standard error of the sampling distribution of the difference between all sample means of all samples that are extracted from both parent populations, which could number in hundreds of thousands or millions. This would be the standard error. And notice that to compute the standard error, we do know the population standard deviations. All right, that's why we call this a z-test, because this variant is normally distributed according to the normal distribution. All right. So, in other words, if we got like population 1 here and we got population 2 here, there's a lot of different samples you can choose from each of these populations. Suppose we choose one sample from population 1 and we compute its mean. That would be called x of 1 bar. Suppose we choose a sample from population 2 and compute its mean. That's called x of 2 bar. And then later on, what we would do is take the difference between these sample means here. Well, we could choose a whole bunch of different samples from populations 1 and 2 and compute their means and compute the differences between the samples. And so what happens is, according to the central limit theorem, that said sample means chosen from one population are approximately normally distributed. Well, that carries over to the distribution of the difference between all sample means that could be chosen from the different populations here. So we have a whole bunch of differences here. Okay. Whole bunch of differences here. And each difference would be different than any other difference. But if you were to build like a histogram of all these different differences between the sample means of 2 samples chosen from each respective population, these differences in these sample means would be approximately normally distributed. Okay. And that is guaranteed by that central limit theorem there. All right. And this would be the standard deviation of that sampling distribution. Okay. All right. So this standard error is like the sum of the variances or the sum of the standard deviations of the sampling distribution here. Okay, so it's kind of like a pooled standard error, if you will. To use this test statistic, of course, your hypotheses will, your null hypothesis is going to look like this for testing 2 population means for their difference. And of course, the alternative hypotheses will have the not equal to symbol, greater than, or less than symbol. and you'll have 0 on the right side here. So again, this particular hypothesis test, the alternative hypothesis would be saying that the mean of population 1 is not equal to the mean of population 2. This alternative hypothesis would be saying that the mean of population 1 is greater than the mean of population 2. And finally, this one here would be saying that the mean of population 1 is less than the mean of population 2. So this would be a two-tailed test. This would be an upper tail test, and this would be a lower tail test. Okay. And of course, the hypotheses for the proportions are similar. There's no difference. The only difference is we'd be testing the difference between population proportions as opposed to means, but everything else is the same. Okay. Here's an example. 40 men and 40 women found that the average daily intake of sodium for men was 3,653 milligrams, and for women, 3,482 milligrams. Okay. Assume that the population standard deviations for the previous studies is 324 milligrams for men and 287 milligrams for women. At the 5% level of significance, can we conclude that the difference in average sodium intake is significant? In other words, is there a difference between the average sodium intake between men and women? Well, this would be a two-tailed test. The hypotheses would be these. The null says that essentially there is no difference between the mean sodium intake between men versus women. Which was which here? Okay, it looks like they designated population 1 to be from men and population 2 to be from women. It looks like that's the designation they chose here. Being a two-tailed test, ladies and gentlemen, it doesn't matter what order of subtraction you have between the sample means for the test statistic, because you have 2 rejection regions. You have one in the lower and the upper tail. So whether your test statistic is positive or negative doesn't matter, because if it falls in the upper tail rejection region, if you switch the order of subtraction, it would just fall in the lower tail rejection region. Okay, that's one nice thing about a two-tailed test. You don't have to worry about your order of subtraction here. But they chose the order of going with men minus women here. And the alternative hypothesis would be saying that the mean sodium intake of men is not the same as the mean sodium intake of women. So these are the hypotheses we're testing. We're going to have 2 critical Z values, one for the lower rejection region, one for the upper rejection region. And of course, those are determined by the level of significance that we test at. And we're testing at 5%, which means that both the lower and upper tail get half of the 5% for its area, which is to say 2.5% would be the area of the lower and upper tail rejection regions. Okay. And so that's going to leave 90% of the area of the entire normal distribution curve to be the do not reject region in the middle here. Right. All right. Now, to compute the test statistic, we basically substitute our values in where they belong. The mean, the average of the male sample of sodium intake was 3,653 milligrams, minus the average of the women sample was 3,482 milligrams, minus 0. Where does the 0 come from? 0 comes from the assumed difference between the unknown population means under the null statement, which says that the difference is equal to 0. That's where that 0 comes from, because this is under the null statement here. Divided by the pooled standard error, which is the square root of the ratio of the square of the standard deviation of the population, which is known, divided by the sample size, and you add those together there. So if you get on your calculator and you dial this up, you should get a test statistic value, which is about 2.50. And of course, we need to establish our rejection acceptance region. So our critical Z values by using your inverse norm function would be found to be a positive 1.96 and a negative 1.96. And we can see, ladies and gentlemen, that our test statistic 2.50 falls safely in the upper tail rejection region because it's greater than 1.96. And therefore, at the 5% level of significance, we are going to reject the null hypothesis. And therefore, we will conclude that, yeah, it appears that there is a difference between the mean sodium intake for men versus women. There is a difference. In other words, the mean sodium intake for men is not equal to the mean sodium intake for women. Okay. And so in rejecting this null hypothesis, of course, we stand a 5% chance of committing a type 1 error, rejecting a null hypothesis that may in fact be true. But 5% is usually not a ton of risk. And so we would definitely lean towards rejecting the null here and not fret too much about it, okay? Of course, this is the critical value method for conducting this hypothesis test here. I always recommend drawing the picture of the normal distribution and showing the rejection, do not reject regions, and also the critical values. Your author doesn't do that, but I think that's a very, very helpful step to put in, is to actually draw a picture that illustrates your reject versus do not reject regions. All right. Any questions how this true population mean Z-test was conducted manually using the critical value method here? And you can see the test statistic is a little bit more complicated than if we just are testing one population mean, okay? Other than that, everything else is pretty much the same. The steps really don't change in general. All right. Now, that, of course, was the critical value method. Maybe what we could do is do this on the calculator now to show ourselves how it would be done. So we will bring up the calculator and show you how the p-value method could be employed in testing these hypotheses here. All right, so to do this on the calculator, we will go to stat, go to tests, and this is going to be a 2-sample Z-test, okay? So 2-samp Z-test is the function we're going to use. Okay. So we will dive into the 2-sample Z-test. And we have our choice of, whether we have raw data sets or stats computed for each sample. We do have stats computed, select stats. And now we need to fill in these fields. So what is the population 1 standard deviation? Well, it is known to be 324. That's for the male population. For the female population, the standard deviation is known to be 287. The male mean amount of sodium intake from the sample that we selected was 3,653 milligrams. The size of the male sample was 40. The sample mean sodium intake from the female population was 3,482. And the female sample size was the same as the male, 40. Do these sample sizes have to be equal to each other? The answer is no, they don't have to be. All right, in this case, they were. This is going to be a two-tailed test, so we select not equal to for our alternative statement. And we go down and just calculate, lays on, and we're ready to conduct this two-SAMP Z test, okay? And we get our test statistic, which is 2.4986, about 2.50. The p-value is about 1.2%. And notice your p-value is less than 5%. Being the case, we will reject the null hypothesis at 5%. Notice we could not reject at 1% because our p-value would be a smidget larger than 1%. But we could drive alpha down all the way to 2% or even 1.5%, and we would still be able to reject at 1.5% level of significance. So this is overwhelming evidence to suggest, ladies and gentlemen, that we would definitely want to reject the null hypothesis, and we would not have to worry about committing a type 1 error. The risk is very low. Okay. All right, so that's how we would conduct this test using the p-value method, using the two-SAMP Z test function on our calculator. Any questions how we did this test, either manually or using the p-value method? Okay. All right. Just like we constructed a confidence interval for an unknown population mean using one population, we can also do so for two population mean, for the difference between population means. We can construct a confidence interval. And this would be the formula that you would use to construct a confidence interval for the difference between the means of the populations. All right. Notice we have our standard error that appeared as in our test statistic formula. And of course, we have our critical Z values that also are needed for our to compute our margin of error here of our confidence interval. So to find a 95% confidence interval for the difference of the means using the information from the previous example with the critical Z value of 1.96, we would put the numbers in where they belong into the formula. Again, this is reverting back to the example we just did with the hypothesis test. And this would be the lower end point of your 95% confidence interval. And this would be the upper end point of your 95% confidence interval. All right. And okay. And so, ladies and gentlemen, we get our confidence interval here. And so we are 95% confident that the mean sodium intake for men is different than the is different than the mean sodium intake for women. Now, here's how we know there's a difference here. Got a question for you. Is 0 in this interval here, this confidence interval? Is 0 contained in this interval? Would 0 lie between 36 and about 305? Yes or no? What do you think?
No.
0 is not in this interval. And because 0 is not in this interval, is the difference between the population means could never be 0. And we say that with 95% certainty. So that indicates that there is a difference between these population means because 0 is not contained in the interval. Very important observation there. So the 95% confidence interval corroborates with our hypothesis test. Both are indicating that there is a difference, okay, between the mean sodium intake between men and women. All right. Okay, so that's how you would build a confidence interval. So we would say that the difference in the mean sodium intake between men and women would be between 36.86 milligrams and 305.14 milligrams of sodium. I have a question for you. Based on the endpoints of this 95% confidence interval, based on the fact that both these endpoints are positive, it looks like the mean sodium intake would be greater for who? Men or women? Based on our order of subtraction we used up here. What do you think? In other words, we're 95% confident, ladies and gentlemen, that this difference lies in what? That this difference is in this interval. Do you agree? And because both endpoints are positive, that would indicate that which mean is larger? For men or women? This would imply, because you're taking the men mean, subtracting off the women mean, and the endpoints are positive, that would suggest that the mean sodium intake for men is greater than the mean sodium intake for women, because you have positive endpoints. If both these endpoints of this interval were negative, we would say just the opposite. The mean sodium intake of men would be less than the mean sodium intake of women. Does that make any sense? Just by looking at the signs of the endpoints of the interval. You can tell us or give us an idea as to which mean is larger. Okay. All right, here's another one. Researcher hypothesizes that the average number of sports that colleges offer to men is greater than the average number of sports offered for women. A random sample of 50 colleges shows an average of 8.6 sports for men, 7.9 sports for women. Assume that the standard deviation of the number of sports is 3.3 for men, for both men and women. Interesting. Can we say at the 10% level of significance that there is enough evidence to support this claim? And what would be our hypotheses? Well, it comes from greater than. Greater than means that our alternative hypothesis statement would be greater than 0. Therefore, the null statement would say that the mean number of sports for men, the difference between the mean number of sports for men and women is essentially equal to 0, meaning there is no difference. Versus the alternative statement is saying, yes, there is a difference. Particularly, the mean number of sports for men offered for men would exceed the mean number of sports offered for women at colleges. That's what these hypotheses are saying. Statistic-wise, we have our same formula, and we have to substitute in the means of the samples that were chosen from the parent populations. Of course, this guy is going to be the purported difference between the population means under the null, which means that's why this is 0. Put in the known standard deviations of the populations, divided by, square those and divided by the sample sizes, and we get a test statistic that's 1.06. Ladies and gentlemen, it looks like they conducted a p-value test for this and found the p-value to be 0.1446. Is this a large or small p-value? This p-value right here. About 14.5%. Is that
Large.
that's pretty large, isn't it? I mean, that's getting up there as far as the risk is concerned, as far as rejecting a null hypothesis. I would probably not want to reject the null hypothesis for this hypothesis test here. That's too much risk. You'd have to drive alpha's value up to at least 15% or higher before you can reject the null. and say that, well, the mean number of sports offered to men exceeds that for women. It doesn't look like the claim is being supported here, this being the claim, because that p-value is too high. Okay. So yeah, too much risk there. Don't reject the null there. So that's an upper tail test conducted via the p-value method. And this is just showing you on the calculator how to take care of business. Let's see here. Oh, I want to show you how to build a confidence interval, ladies and gentlemen. Let's go back here. Remember, for the problem which dealt with the sodium intake, okay, the mean sodium intake of men versus women. Let's show you how to build a confidence interval on our calculator instead of having to go through this manually. So let's bring up our machine. Okay, and we go to stat, tests. But to build confidence intervals, we don't use the two sample z-test. We go down and use the two sample z-interval function. There you go, the two sample z-interval function builds a confidence interval for the difference between the population means. Select the two sample z-int function to build a confidence interval. Of course, we have stats already provided for us. Hey, you know what? I think, look what happened here. This is interesting. Because we conducted the two sample z test, we entered all the information in and transferred it right over into the two sam z int function. Isn't that cool? We don't have to retype all this stuff in. Well, that's a time saver. And our level of confidence is 0.95, 95% level confidence, and calculate. It's that simple. Everything's been entered in already. Hit enter. And boom, there you go. There's your confidence interval, lower endpoint of which is about 36.86, the upper endpoint of which is about 305.1, well, 1314. Okay. As I mean, where you round these endpoints off is not going to make a bit of difference as to our overall conclusion regarding this confidence interval and what it's saying. Whether you call the lower endpoint 36, just 36, call the upper endpoint 305, or include these decimal digits, doesn't matter. The bottom line is 0 is still not going to be found in this confidence interval. And the bottom line is both endpoints are still positive, which suggests that the mean sodium intake of men exceeds that of women. Okay? So that's how we build a confidence interval for the difference between population means. You use the two sam z int function. All right, so let's see if we can go to our textbook and do maybe a problem or two. Let's see. And of course, these problems will be done in section 9.2. And 9.2 is entitled Testing the Difference Between Two Means Using the Z-Test. And as always, feel free to look down through this section if you want to maybe solidify this. This is nice. This table's nice here because it kind of groups together, you know what I'm saying, all of your tests here. The symbolism used for the hypotheses to represent the various tests here. Two-tail test, right tail or upper tail test, left tail or lower tail test. All right. Making sense there? Right there. Okay. There's your sodium intake problem. We already did that there. But your author does a nice job in the textbook in showing you the rejection regions in the upper and lower tail, the standard normal distribution, and the critical Z value. So yeah, I always recommend, please do draw a picture of the rejection, do not reject region. It helps you to better understand what your decision is. Kind of bummed out that they did not do that on the PowerPoint presentation, but it's in the textbook here, right? If nothing else. All right, let's see here. Oh, this is interesting. Ladies and gentlemen, for the you remember the college sports offered for males versus women? Uh, on the PowerPoint presentation, they just gave us the statistics, didn't they? Already computed. The sample means were already computed. But here they're giving us the raw data sets. Look at this. So these are random colleges that offered so many different sports for males and females. These are the raw data sets here. And if you were to compute the mean of this male data set, you should get what, 8.6. And for the female data set, if you compute the mean, you would get 7.9. Standard deviations in the populations, of course, were given to us as 3.3. And you would conduct your hypothesis test. Now, I have a question here. What would be the only difference in how we would conduct this hypothesis test, the p-value method on our calculator, if we used the raw data as opposed to already computed sample statistics? What would be the only difference in how we conduct a p-value test? We would not select what? Stats. We would select what if we just typed in all the data? Like in list one, maybe put male data, list two, female data, and then did the hypothesis test for the population mean differences. We would have to select not what data, excuse me, we'd have to select not stats, but what data. Do you agree? That'd be the only difference. And we would still get the same outcome. Nothing would change. Okay. All right. Well, that's an interesting investigation there. American National League here. Let's see what they're doing here. Okay. For a sports podcast, you are asked to research the question of whether more home runs are hit by players in the National League or by players in the American League. So, Lazo, we could test these here using the raw data here. These are the number of home runs hit by, let's see, various players in each league. Okay. Are the mean number of home runs hit by players in the National Leagues greater than the mean number of home runs hit by the players in the American League? Tell you what, why don't we do this for our classwork right now? So the hypotheses are going to be what? Null would say that the mean number of home runs hit by the National League minus the mean number of home runs hit by players in the American League is equal to what, 0? Versus the alternative hypothesis would say what? What do you think? Is greater than 0, correct? Greater than 0. Do you agree? Those would be the hypotheses we'd be testing there. And go ahead and do that. I want you to put this data in list 1 and put this data in list 2 and then conduct a 2-sample z-test. Okay, testing these hypotheses. Go ahead and do that and use your p-value to make a decision. All right, so we'll call this a classwork, okay? Go ahead and do that problem. All right, so now when this test was conducted here, we were gonna conduct an upper tail test here. And let's see. All right, so did anybody get a p-value when conducting the upper tail test? They conducted a two-tail test for the difference between the population mean home runs between the two leagues. And they got a p-value which is about 0.3124, which is a very large p-value. So there's no way you would reject the null hypothesis here. And essentially, you cannot conclude that there is a difference in the mean number of home runs hit by the National League versus American League. Not according to this hypothesis test, this two-tail test they conducted here. And we should have also gotten a very large p-value for our upper tail test. Do you agree? Not being able to reject the null hypothesis. So it doesn't look like the claim is being supported here that the National League hits more home runs than the American League. It's just not being supported at all. P-value is way too large. Too much risk in rejecting the null hypothesis here. Way too much risk. Okay. Did anybody conclude that with a large p-value?
Yep.
Okay, now let's see here. All right, problem number 5. I would like you to conduct this problem, ladies and gentlemen, 2 ways: using the critical value method and also using the p-value method. Sodium content of popcorn. The mean sodium content of movie popcorn is 980 milligrams of sodium per container. A researcher randomly selects 2 samples of 30 containers of popcorn from 2 different movie theaters and finds that the mean sodium content from theater A was 973 milligrams versus the mean sodium content from theater B was 968 milligrams. If the population standard deviation of sodium content is 9 milligrams, we're assuming the population standard deviations for both theaters is 9 milligrams. Test the claim that there is a difference in the sodium content of the popcorn containers from the 2 theaters and test at 5%. Okay. All right. I would like you to show the 5-step method, the critical value method, show all the steps, and then use the p-value method on your calculator to confirm your results from your critical value conclusion. Number 5. Have at that one. Okay. All right, so problem number 5 here. This is showing all the steps. Hypotheses we're testing is that the mean amount of sodium found in popcorn in theater A minus the mean amount of sodium found in popcorn from theater B is essentially equal to 0, meaning there would be no difference between the two. Versus the alternative hypothesis that says that there is a difference. That the mean amount of sodium from popcorn containers from theater A is not equal to the mean amount of sodium found in popcorn containers in theater B. This is the claim. Testing at 5%. We're going to have 2 rejection regions being a two-tailed test. Inverse norm would find these critical z-values of being negative and positive 1.96. To test a statistic from a sample of size 30 containers from theater A, the mean sodium content was 973 milligrams. From a sample of size 30 containers from theater B, the mean sodium was 968 milligrams. Now the standard deviation sodium amounts was 9 milligrams for each theater. Test statistic is about 2.15. Where does it fall in relation to our critical z-values? 2.15 falls in the upper tail rejection region, being greater than 1.96. And therefore, we are going to reject the null hypothesis, and therefore it looks like the claim is being supported by sample evidence. So our plain conclusion would be that sample evidence shows that the mean amount of sodium in theater A is not the same as the mean amount of sodium in popcorn containers in theater B. The p-value also confirms that. We got a p-value of about 3.1%, which is less than our level of significance, 5%. Therefore, we reject the null hypothesis. We would not be able to reject the null hypothesis at 1%, not even at 2%. But we could reject our null hypothesis at like 3.5%. So bottom line is the risk is pretty low for committing a type 1 error here. So I would definitely lean towards rejecting the null hypothesis. Okay. All right, ladies and gentlemen, did anybody get that, these results? Yeah. Okay. All right. Okay. All right, how about a confidence interval problem? Let's try one of those. And there is one for us. Problem number, let's see here. Number 21 is an interesting one. 2 brands of batteries are tested and their voltages are compared. The summary statistics follow. Find the 95% confidence interval for the true difference in the means, the population mean. And this is the voltage of the battery. Assume that both variables are normally distributed. So there's all the sample evidence there. So they tested 27 or measured the voltages of 27 batteries from brand X batteries and found the mean voltage to be 9.2 volts. Standard deviation voltage is 0.3 volts. It's known from the population. 30 brand Y batteries that were measured, the average voltage was 8.8 volts and the standard deviation was 0.1 volts. And so what I want you to do is for a classwork problem here, is I want you to build a confidence interval for the difference between the population means. Okay. In other words, I want you to compute a 95% confidence interval for the mean voltage of the brand X battery, the difference between the mean voltage of the brand X batteries and the mean voltage of the brand Y batteries. Go ahead and construct that confidence interval. And you can just use your calculator and use this 2samp z int function. The 2sample z int function. Go ahead and do that. And we'll take a look at what you got there. Okay. All right, so you're going to use the two sample Z interval function, and this is how you would configure it. You select stats because we don't have any raw data for both of these samples. We already have the sample stats computed. The standard deviation for the brand X batteries is 0.3 of a volt. For the brand Y batteries, the voltage standard deviation is 1/10 of a volt. You enter in the mean voltages for the various batteries and the sample sizes for each of those. Notice the sample sizes are not the same. Select your level of confidence, which is 95%, and away we go. So let's hit enter. And that would be your 95% confidence interval for the difference between the mean voltages of brand X batteries versus brand Y batteries. Now I have a question for you. Both of these endpoints of this 95% confidence interval are positive or negative? What do you think?
Positive.
Both positive. So I have a question. Would zero be found in this interval? Is zero in between these endpoints?
No.
Nope, zero's not in there. Because zero's not in there, that would indicate that the difference in the mean voltages of these two different batteries, okay, is not equal to zero. Meaning there is a difference. Okay, there is a difference. Specifically, what difference would exist? Notice my order of subtraction was brand X minus brand Y. Specifically, the means were subtracted in this order here. And since we have endpoints that are positive, that would indicate that this difference is what? Greater than zero, isn't that true? Which would imply then that the mean voltage of what battery exceeds the mean voltage of which battery? It looks like the mean voltage of the brand X batteries would be what? Greater than the mean voltage of the brand Y batteries. based on, again, the fact that our confidence interval has positive endpoints. And we did this order of subtraction here. That was the order of subtraction we chose. And so obviously this mean has to be larger than this mean if you are to get a positive difference, as indicated by the endpoints of the confidence interval there. All right, did anybody get that confidence interval? Right here. Did we
Yeah.
get that? All right. Okay, you know, that covers today. We looked at how to build a confidence interval for the difference between two population means where the standard deviations are known, and also how to build a confidence interval for the difference between those unknown population means. Next week, we'll continue investigating two sample hypothesis testing, but we'll be testing for the difference between population proportions as opposed to means. All right, so have a good Thanksgiving, and I will remain on the line if there's any questions or comments of anything. If not, hopefully I'll see you next Monday. All right, take care.